Okay, today now we will discuss about how to draw a crank and slotted lever mechanism velocity diagram, and why we are discussing. First of all, we will try to understand why we have to discuss. Okay, so this is crank and slotted lever mechanism, and here this is a quick return mechanism. We have discussed how it will work. So this is the link OA is a fixed link, and here there is a slider. Okay, here there is a slider, and this crank, suppose this will act like a crank, and this will rotate in full rotation 360 degree and this is a hinge joint R, and we will connect one more link, and here we attach a cutting tool, and this is the slider, so the cutting tool will move. Okay, if the crank rotates, this will move in this forward direction. So this is a fixed link G, and this is a slider S. So this is the quick return mechanism, and we understood how it will work, okay, in the last chapter, and why we need to discuss more in detail to construct this velocity diagram. Because here when this is a hinge joint and this is a slider, and AR is a link, which will be, AR is a guide, okay, and there is a slot here, okay, on this AR link, and this slider will move like this. Okay, so here this, because this link is rotating with omega and it is attached with a hinge joint, this slider, so what will happen, this slider is also having angular velocity, okay, because we attached at the end of the crank. And also this slider cannot move out of this link AR, and it will move like this. Okay, it will move along this link AR. So here it is this sliding block is having linear velocity, and also it is having angular velocity. Because actually it is if you want to find the absolute velocity of this slider, okay, it is more complicated, right? So you need to understand what is the angular velocity of the slider, because this slider is having both angular velocity and also linear velocity. So for this, what we will assume, we will just try to make 2 points. Okay, so one point P on slider, P is a point on the slider, okay, and we can assume another point Q, which is on link AR. Okay, we assume 2 points, okay, one is on the slider and Q is on the link AR, and both P and Q are coincident points. Okay, both P and Q are coincident points. So what will happen here, actually when we assume like this, actually this is a single point, and actually this Q is on this link AR and P on this slider. So P is having some this is the point on the slider, and Q is on the link AR. Okay, so once if you assume like this, actually we can construct the velocity diagram, okay, and we can write the equations and all, and we will discuss with example. Okay, the example here, I am taking one example here. Okay, so this one here there is a OP is the crank, okay, which is 200 millimeters, and AR is having 700 millimeters, and RS is the link of 300 millimeters, and crank rotation, okay, crank rotates at 22 radian per second. So that means omega of OP, okay, PO, omega of PO or OP, it is 22 radian per second. And now actually you have to construct the velocity diagram for this. Okay, the problem here actually first you have to calculate the velocity of cutting tool. Okay, and second one, the angular velocity of RS link. Okay, so you need to find these things. So we will try to draw the configuration diagram first. So I am choosing a scale of because actually we have to choose one scale. So I am choosing a scale of for space diagram. Okay, scale I am choosing 1 centimeter is equal to 100 millimeter. Okay, so now we will construct the space diagram. So first we will draw one vertical line which is a fixed link. Okay, so this problem related to the crank and slotted lever mechanism. So we will we know how the mechanism will look like. Okay, so we will try to understand OA. OA is 400. Okay, I forgot to mention here. OA is 400 millimeters. Okay, so we will try to draw one vertical line of 4 centimeter. Okay, 4 centimeter, and we will mark this is A and this is O, and they have given 120 degree. Okay, I will draw roughly whatever the figure they have given here in the problem. Okay, so this is the fixed link. Okay, so this is a rough figure of the mechanism in the problem. Okay, so this is 120 degree, and okay, so this is 120 degree, and here AR is this one. Okay, so here there is a slider and there is a crank, there is a link, and here they have attached slider, and this is G point, and you can take this is 60 degree. Okay, so this is a rough figure, and I am drawing a space diagram by using some scale. So OA we have drawn for 4 centimeter, and this is a fixed link, and now we will measure 120 degree here. Okay, so this is 120 degree, and here 120 degree OP. P is the point on the slider. Okay, P is a point on the slider. So OP is 200 by 100, it is a 2 centimeter. Okay, so you have to draw a 2 centimeter line. Okay, so this is our P point. Okay, and you can make a thick line here, and this is 120 degree. Okay, and now RS is AR is 700, that means 7 centimeter. Okay, 7 centimeter. So you can connect these 2 points, this A point and this P point, okay, to and draw a line here, and this is 7 centimeter. Okay, so this is R point, and from here you measure 60 degree. From here you measure 60 degree here. Okay, and RS is 300, so this is 3 centimeter. So you can draw a thin line and mark 3 centimeter. Okay, so this is the slider. Okay, you can mark like this. Okay, so this is also a slider like this. Okay, so this is a crank and slotted lever mechanism. So from this we will try to understand how to draw a velocity diagram. So first we assumed a P on the slider. Okay, we assume 2 points, P on slider and Q on link AR. Okay, so to construct the velocity diagram, first of all we know that this is rotating clockwise with the omega. Okay, so link OP, why I am writing link OP? Because P is on the slider. Okay, P is on the slider, so it is also having you can calculate V of P relative to O. Okay, velocity of P relative to O, this is 200 into 22, so this is 4400 mm per second. So to construct the velocity diagram, we choose one scale. So I am choosing a scale of 1 centimeter is equal to 1000 mm per second. Okay, so here we will draw a perpendicular line. Okay, this is the magnitude. Okay, so our scale, according to our scale, OP vector length will be 4.4 centimeter. Okay, and direction is perpendicular to link OP. Okay, we know that. Okay, so now we will try to draw the velocity diagram. So here to draw this, how many fixed points are here? Actually A, O and G, there are 3 fixed points. So we will take as 1 point with small letters A, O and G. Okay, so now we will draw a perpendicular line to link OP starting from O of the magnitude 4.4. First I am drawing like a thin line. Okay, I am just marking 4.4. Okay, so this is the direction when the crank is rotating like this. So this is the direction and this is the P point. Okay, what else we know here? What else we know? We can say that the slider, okay, the slider can move like this when this crank is rotating like this. So we can draw a parallel line. Okay, we can draw a parallel line to this S from starting from G. Okay, so you have to draw a parallel line. Okay, so this is a horizontal line. Okay, from G you can draw. Okay, so this is represent anywhere on this line there is exist S point. Okay, so now what we will do, actually we can say that this to locate Q point. Okay, to locate Q point, what we will do, we will draw perpendicular to AR from A, because Q on link AR. So we know that actually the link, this link velocity is perpendicular to this link AR. So first we will draw a perpendicular line to link AR. Starting from A. Whether this is correct? Okay, so on this link, okay, on this line there exists Q. Okay, there exists Q. So one more thing you have to understand here, P on the slider, okay, and Q on link AR. This Q point will move like this because it is on the link AR. Okay, so now you can draw a parallel line to AR from P. Okay, so we will draw a parallel line to this AR from P, and the intersection point will be Q. Okay, the intersection point will be Q. Actually, whether we draw a correct line here, I'm not getting. Yeah, we draw one. This is the line, parallel line to S. Okay, so this is the parallel line to S. Okay, so now this is the Q. And you can say, you can mark thick lines. Okay, you can mark thick lines. So now to get the direction, okay, so P and intersection is Q point. Okay, so to get the directions of these vectors, you can write the equation V velocity of Q, which is on link AR relative to O, okay, relative to O, will be equal to velocity of Q relative to P. Okay, Q is point on the AR link and P is on the slider. Okay, plus now the velocity of P relative to O. And anyway, O and A are fixed points, so this will be equal to velocity of Q relative to A. So in vector forms, OQ vector will be resultant of PQ vector plus OP vector, and this is also equal to AQ vector. So OP vector we know completely, okay, the direction, and OP vector plus PQ vector. So it is in the same direction like this, okay, and this AQ or OQ vector will be the resultant. Okay, will be the resultant. So now what will represent PQ? PQ will represent velocity of sliding block. Okay, this is the velocity of sliding block, this block PQ. Okay, PQ will represent the velocity of the sliding block on link AR. Okay, so you can calculate this one by measuring this. So our question is velocity of the cutting tool. So now slider, cutting tool means it is this one. Okay, yes, you have to find. And now to locate S, okay, to locate S, you have to locate R point. Okay, to locate S here, you have to locate R point here. So how to locate R point? If you observe this, you can say that there is a link like this, and this is A, and you assumed this is a Q point and this is R point. So what you can say here, there is one link here, and Q is on the link, okay, or otherwise on the link AQ, R is the point. Okay, so how to locate R here? So you can write AR by AQ is equal to AR by AQ. Okay, so now AR you can calculate, it is AQ into AR by AQ. So now you can measure this. You can measure this AQ vector. It is nearly 4.4. Okay, 4.4 into our scale is 1000 into AR is 700. AQ, how you will measure? So this is the Q point, right? So this is the Q point. So from space diagram, from this point to A point, you can measure, and this is I am getting 5.4. Okay, so 5.4 into our space diagram is 100. 1 centimeter is equal to 100 millimeters. So you can calculate this. Okay, so 4.4 into 1000, it is 440 into 700 divided by 540. So this is 570.4. Unit is velocity here, so mm. Okay, so here we made a mistake here. It is AQ vector. Okay, AQ vector is not 4.4. Okay, please, I'm just AQ vector. It is 3.4. Okay, it is 3.4, not 4.4. Okay, so this is 3.4. Okay, so 3.4 into 1000. So 3.4 into 1000 is 340. Sorry, 3.4 into 700 divided by 540. So this is whether we are getting correct. 3.4 into 1000 into 700 divided by 540. Okay, so this is 4,407.41 mm per second. Okay, 4,407.41, and if you convert into our velocity diagram, divided by 1000, this is 4.4 centimeter. Okay, so this is 4.4. This is a AR vector. So from A you can mark 4.4. Okay, you can mark this is R point, and you can make a thick line. Okay, so this is a R point, and the direction of AR vector is in the same direction of AQ. Okay, so because R is a point on the link, okay, on the link. Okay, anyway we calculated AQ direction. Okay, so now here how to locate S here? Yes, you have to draw a perpendicular line to this link RS, starting from R. Okay, so you have to draw a perpendicular line to link RS starting from R. Okay, so this is a parallel line to this S. Okay, so this is the intersection will be S. So draw perpendicular to RS and draw parallel to S. So intersection will be S. Okay, so you can draw a thick line. So this is the velocity diagram for this crank and slotted lever mechanism. And now how to locate the directions of these vectors. So again we will write the equation. So velocity of S, okay, velocity of S relative to A, okay, velocity of S relative to A will be equal to velocity of S relative to R, velocity of S relative to R plus velocity of R relative to A. Okay, so you can in vector form, AS vector is the resultant of RS vector plus AR vector. Okay, AR vector you know completely. Okay, this is the direction plus RS vector. So AR vector in this direction. So this RS vector will be like this, and AS vector will be closing side. So like this we will mark. And now first question is velocity of cutting tool. Okay, so cutting tool is the velocity of S relative to G or any fixed point, right? So you just take a scale and measure this. This is 4.1. Okay, I will take a compass, that is a better thing. Okay, because no error. Okay, we can minimize the error. Okay, yeah, I am getting 4.1. So this is 4.1 into 1000. Okay, our scale. So 4, okay, 4000, this is 4100 mm per second. Okay, that means actually when the crank OP is rotating with 22 radian per second, okay, this cutting tool will move, okay, with 4100 mm per second. So this next one, angular velocity of link RS. How we calculate? This is VRS, velocity of a RS link, divided by RS, length of the RS. So velocity of the RS, again take a scale and measure this. So this is the thing, okay, RS link. Okay, so this one measure with the compass. Take a scale and measure how much. And this is 1.5. Okay, so 1.5 into 1000 divided by RS is 300. Okay, so this will be 1500 divided by 300. So 5 radian per second. Okay, so like this we will try to construct the velocity diagram for crank and slotted lever mechanism, and hope actually this one is important because the slider is having the angular velocity because it is attached, okay, with this crank, and also the slider will move along this AR link. So we will choose 2 points, and one point on the slider and another point on the link AR. So both are coincident points, and we will try to construct the velocity diagram.